We had discussed semi-simple Lie algebras and simple Lie algebras, and also talked about uh, what direct sum and semi-direct sum of Lie algebras mean. Now, they are going to be important in today's context, these issues. But before we go there, let's talk about something which is actually very practical. You need to do it when you study the theory of Lie algebras, which is something called complexification of a Lie algebra. In other words, so far we have been dealing with real Lie algebras. Of course, a real algebra is a real vector space on which you have this bracket operation. And of course, because you're doing bracket operation between real elements and the resulting vector is also real, all the structure constants would definitely be real there. Could of course also talk about complex Lie algebras. Complex Lie algebras would be things where you have a complex vector space to begin with, and you could define a bracket between those complex elements, those complex vector space elements. And as long as you have anti-commutating property, linearity, and Jacobi identity, you're good. You have a genuine Lie algebra. However, you must realize that although we are not focusing on this as much as possible, but as we have already seen, to us, Lie algebras really are things we work with because they came from a Lie group. And in a Lie group, you basically have a bunch of real parameters, and the corresponding Lie algebra which comes out of the theory of Lie groups is the real Lie algebra. So although you could very well have a complex Lie algebra ab initio, usually you start out with a real Lie algebra when you're working with things, especially when you're trying to study the properties of a Lie group through its algebra. Complexification is a process which starts with a real Lie algebra and changes it, so let's call that L, and changes it to a complex Lie algebra, L tilde, by a well-defined procedure. Okay? So first step here is, in a complex Lie algebra, of course, the underlying vector space is a complex vector space. The vector space where the scalars are complex numbers. In a real Lie algebra, the underlying Lie algebra, of course, is a real vector space. So the first step that is there in this complexifying process is complexifying the underlying vector space. What that means is you had a real vector space, a vector space where the scalars were all real numbers. You want to somehow convert that into a vector space where the scalars are all complex numbers. And the way to do that should be sort of obvious. This is the way in which you build up complex numbers from real numbers, the same idea. The idea is, let's say you have two elements, x and y, both of which belong to L. This L, right now we are focusing on the underlying vector space of the Lie algebra. So these are, of course, Lie algebra elements, but at this point we are focusing on their vector character rather than so much on their bracket. So this is x plus y belonging to L. This will give us an element, single element z of L tilde, which is defined to be x plus iy. Okay. Now you might very well ask, what does I mean? I, of course, to us means square root of -1, right? As a standard meaning of the letter I for us. However, if you took that literally, you would be in a bit of a problem, because since our vector space L is a real vector space, I don't even know how to multiply its vector by an I. All I'm saying is just define x plus iy to be an element. Or if you want to be more formal, you don't even have to write this as x plus iy. You could just say pairs of elements of L make an element of L tilde. This should already be familiar to you from the theory of complex numbers, where you might have first encountered complex numbers as something of the form x plus iy, where I is square root of minus 1. And then it might become a bit sort of iffy, because what does square root of minus 1 mean? And is it at all sensible to talk about things like that? Is it at all sensible to multiply y by square root of minus 1? This kind of questions might very well come to mind. But what Hamilton did in the theory of complex numbers was actually formalized it. The same Hamilton, by the way, the great Hamilton of the Hamiltonian and quaternion, etc. He actually first put complex numbers in a firm footing by showing that instead of dealing with this complicated square root of minus 1 kind of thing, which many people had a problem with, you just talk about pairs of real numbers, and you can define pairs of real numbers with addition multiplication properties in such a way that you are going to actually end up with the square root of minus 1 automatically at the end of the process, while dealing with real numbers all the time. So you don't have to really go out and invent new things. You would just have real numbers, pairs of them working, and it will work out. That was what Hamilton did. So following Hamilton, what we could do is, we could have to do the same thing with our vector space. X by here are of course not numbers, they are elements of the vector space. Put say a pair of them together, make my complex vector. Or you could just sort of forget bothering about that and think of x plus iy as just another way of talking about this pair. Yeah? So these are the elements of my vector space. So how do you define multiplication and addition by a scalar and addition? Well, one thing we have to do is addition you have to define, and that's pretty straightforward. X plus iy, this is one element of my complex vector space. Added to x prime plus iy prime will simply be x plus x prime plus I into y plus y prime. Or if you think of this in the pair language, the pair xy added to x prime y prime will give you x plus x prime comma y plus y prime. Perfectly legitimate thing, no problem in defining it. And multiplication of x plus iy, this vector, by a scalar of the form a plus ib. Now we are talking of complex number. Remember, we are talking of complex vector spaces. So we have to have complex multipliers now. Can be simply defined to be ax minus by plus I times bx plus ay. Of course, in all this, things would work out fine if you just stopped having any inhibitions about multiplying y or some vector by square root of minus 1. Treated that like genuinely square root of minus 1 and applied algebra on it, which is exactly what we do when we multiply to complex numbers, right? We multiply x plus iy into u plus ib, as if we were multiplying using ordinary rules. So as we multiply any number, use distributivity and then use the fact that minus 1 is the square of I, right? So you could either say we are defining this specifically, or we could say we are just somehow allowing you to multiply by I, and once you accept that as a legitimate thing to do, everything else will fall in place.
Yes, sir.
Yeah.
The
Yes.
I on the right hand side, that is not scalar I, right?
It is, because now your scalars, what are your scalars now? It is a complex vector space, right?
Yes.
So I, square root of minus 1 is very much a complex number. Remember,
So
this is also a scalar, right? This one is a complex number. This is this new kind of element which I have cooked up.
so even in the x plus iy, the I is root minus 1 by definition.
Well, if you pretend that it's root minus 1 and use it, it will work out fine. That's exactly what this will give you, right?
Yeah, my question
If
is in
you,
a plus ib, that I is definitely root minus 1, right? Because that's the
yeah,
complex.
but then you have to realize when you say a plus ib, before you learned complex numbers, you had this huge issue about what does it even mean when you multiply b by square root minus 1. Maybe that's an issue which you avoided simply because you were taught this and sort of took it on your stride because of familiarity. But
I'm
when
saying
you,
that I in A plus iota B and X plus iota
yeah,
Y
these two are both the
same.
same i's, same i's.
Okay.
And this I is exactly the same I. Same I
Okay.
meaning you're giving meaning to multiplying a real number by square root of -1 when you define complex numbers. And Hamilton gave a formal meaning of this when he did it without using square root of -1 anywhere. He just said take pairs, whose addition rule I'm going to give you, whose multiplication rule I'm going to give you. Then show that everything with like x comma 0 essentially is isomorphic to the real number set, the same multiplication addition rules. And then show that 0, 1 comma times 0, 1 according to his rule of multiplication gives you -1 comma 0, the number
We're
-1.
kind of extending the definition from the
Not extending, he was formalizing the definition of complex numbers, making it
no,
instead
like
of
right
introducing
now
a
are we
square.
like doing an extension of that?
Yeah, right now we are essentially
Mm,
doing that. We are essentially,
yeah.
if you want to make it completely formal without worrying about multiplying y by square root of -1, you can do that. You can just say complex numbers are pairs a comma b, your vectors are all pairs x comma y. You define addition between vectors, you define multiplication of a pair of real numbers with a pair of vectors to give you a new pair of vectors, and everything will work out fine. It's easier perhaps to just think of I as square root of -1 and do it as if it's ordinary multiplication, everything will work out. And at the same time, you will also have to have these rules that if x plus iy is equal to x prime plus y prime, this will imply x prime equals x and y prime equals y. In fact, this implication goes both ways. And another important result that you have to actually assume, although that can sort of be derived out of this, if this is 0, of course, this 0 means the null vector in L tilde, then you must have either a plus ib equals 0, there's a multiplier is a complex number, 0, or the vector x plus iy is a 0. But these two zeros are, of course, different. This is the complex number 0, this is the complex vector 0, which, of course, means x and y are both 0. So with this, we have a complex. Now, the point is we have defined elements of my complex vector space. I've defined how to add them together. I've defined how to multiply them by scalars. What I need to do is to essentially check whether these definitions make this a vector space. That is, whether all the vector space properties are allowed. Okay, are obeyed. Clear? Now that check we can easily do. And I'm not going to waste my time showing you that this is a complex vector space. This is a perfectly easy thing to prove. By the way, you can actually think of L tilde, this bunch of elements of the form x plus iy, also as a real vector space. And that might sound strange, but just bear with me a bit. Suppose E1, E2 up to En, let's say it's an n-dimensional vector space. This is the basis of the original vector space underlying L, which also has the same name, L. L is a name for the Lie algebra, it's also the name for the underlying vector space, it's also the name for the underlying group. Right? So let's say we have a basis like this. Okay. Now every element will be of the form given by E1 into something plus E2 into something. Will every element of L tilde be of this form? The C1, C2 are real numbers. Yes. Every element of L will be of this form. Will every element of L tilde be of this form? With C1, C2 up to Cn being real numbers.
This can be the real part. There should be a different plus
So
alpha.
actually this cannot be every element, but you can actually have ID1 E1 plus ID2 E2 plus ID and En, and it should be really easy to see that every element of L tilde will be of this form, right? Is that okay?
Yes.
Then what we can always do is take the basis to be right, and then every element of L tilde is uniquely represented by a real combination of these vectors, right? Because you are just multiplying each of these by C1, C2, Cn here and D1, D2, Dn here. Clear?
Yes, sir.
So this is the basis of size 2n. So viewed as a real vector space, L tilde will be of dimension 2n, right? However, just think of it this way. You can also think of E1, E2, En as basis vectors, but then E1 will be multiplied by C1 plus ID1, a complex number. E2 will be multiplied by C2 plus ID2, and so on. So now you can think of LTD as a 2n dimensional real vector space, which are the basis of size 2n, namely E1, E2, En, and IE1, IE2 up to IEN, as a real vector space, and now you are combining them with real numbers. On the other hand, you can equally easily think of this as an n-dimensional vector space, but this time the multiplying numbers, the scalars have to be complex numbers. So this is a n-dimensional complex vector space. So just to specify this again, if you start with an n-dimensional real vector space and complexify that, you actually can think of the result as 2n-dimensional real vector space or as n-dimensional complex vector space. We will use the latter because we are thinking of this as a complex vector space. Clear? Next, we have to, of course, now that was just the vector space part. To make it into a Lie algebra, what we have to do is define also the bracket operation. And the bracket operation will be defined rather simply. You will just say if x plus iy is the member of L tilde, which means, of course, x and y are vectors of L, and u plus iv is another member of L tilde, the bracket between them will be defined like this. That again is an obvious extension using the basic property of I times I equals minus 1 and so on. Right? So this is the Lie bracket on L tilde, built out of Lie brackets on L. Okay? Clear? So that's your task. You have to show that this is a valid Lie bracket. That is, it's linear, it's anti-commuting, also there's a Jacobi identity. The proof is actually rather simple. You just have to use the fact that X bracket U, Y bracket V, these are all genuine Lie brackets in L. And the properties of Lie bracket there get inherited here in a rather straightforward manner. Okay. Now let's explore the issue of structure constants. Remember, we have already said in the beginning that if you have a real Lie algebra, the structure constants are bound to be real. And if you have a complex Lie algebra, the structure constants may very well be complex. Of course, that doesn't preclude having real structure constants because real numbers, remember, are also complex numbers. While the converse may or may not be true. May not be always true. So, If you are complexifying L and arriving at L tilde by complexification, then notice that you always have one choice of basis for L tilde available to you, which is E1, E2 up to En, same basis as L. The only difference is now you are allowed to use complex numbers to combine them. But if you use the same basis, E1, E2, En, what will the structure constant be for L tilde? Yes, tell me.
They should be same.
They should be exactly the same, right? Of course,
Yes.
because what are structure constants? You find out the bracket of E1 and E2, expand that in E1, E2 up to En, that gives you CK1, 2. If your basis vectors are the same in both cases, then of course the lead bracket is also the same. You can easily check that E1, of course, is E1 plus I0, E2 is E2 plus I0. So when you take the bracket of E1 and E2 using this formula, you just get E1 comma E2. Everything else will vanish. So basically, the bracket stays the same, so structure constant stays the same. So what you can claim, okay, would it be right to claim then that if L tilde is a complexification of L, a real D algebra, so if is the complexification, because there's only one complexification anyway of a given D algebra. Is this statement correct? I want a response. Is this a correct statement to make?
Yes.
No. This is the wrong statement to make. This is not right. What is right is there exists a basis. Of course, when you say exists a basis, you don't mean that that is the only basis, but at least a basis exists of L tilde. This is the correct statement to make. Let me show you why the previous statement was wrong. You could, of course, change your basis. And in particular, let's say instead of using E1, E2, I use IE1, IE2 up to IEM. Right? Then, so IE1 is my new E1, IE2 is my new E2, and so on. So to find out, say CK1, 2, what will I do? I will take the first basis vector and the second basis vector, namely IE1 and IE2. Bracket them according to our rule before. But our rule before basically is the same as pretending that I is just something and multiply with and squashed minus 1. This is minus E1 comma E2. Right? And remember, in terms of our original structure constant, that this just becomes CK1 to EK. The CK1 to was the structure constants of L, real numbers. So in this case, are the structure constants real or complex? Remember, all you have to do is take the bracket of two basis vectors. Here I've done that. IE1 is the first basis vector, IE2 is the second basis vector. So
This
expand
E1,
that.
E2 they have to be
Hmm?
complex.
What complex of what kind?
Pure
Can you tell?
imaginary.
Purely imaginary, actually. Why? Because although these are negative numbers, negative real numbers, these are not your structure constants. You have to write this in terms of IEK, right? Your basis vector now. So this is actually ICK12, right? So what we have here is a situation where your basis vectors have been changed and you have ended up with purely imaginary structure constant. A statement that if a particular Lie algebra is a complexification of a real Lie algebra, it has real structure constants. That's not right. Structure constants depend on your choice of basis. But all you can say is that there is definitely one basis for which um, the structure constant will be real. But as you have seen right now, there is a basis in which structure constants are not real. They are purely imaginary. By the way, you already have known such a thing all your life because whenever you have talked about angular momentum of commutation relations, you have this I thing stuck in, right? IH cross epsilon IJK CK, right? JK, right? That was JI commutator with JJ. However, the point I'm trying to make here is this. You actually had a real Lie algebra which has been complexified. And instead of using the actual basis vectors, you're using I times that basis vectors and calling those J1, J2, J3. And that is why you're ending up with, despite the fact that you started with a real Lie algebra, three-dimensional, or even better, you started with a real Lie group, a three-dimensional group of rotations, which of course can be described by real parameters. So it's a real one. You started with a real Lie group, and if you looked at the behavior of the real Lie group close to the identity, you would have had real Lie vector space and a real Lie algebra out of that. And what you have done is you have changed that to a complex Lie algebra with complex structure constants by choosing I times, say, x1 as j1, I times x2 as j2, and I times x3 as j3. Where x1, x2, x3 are the original generators or original tangent vectors for the real vector space. Why did I put in I there? There, it was basically dictated by quantum mechanics because the operator representation that you were talking about would be unitary operators for the group, and hence you would want, or hence you can make the generators, basically tangent vectors for that into anti-Hermitian operators. That's what you get directly. But you can make them Hermitian operators or corresponding matrices, Hermitian matrices, simply by putting in an extra I. The I there was motivated more by physics than by maths. You wanted Hermitian operators, so you put in an I. However, you can do that anywhere. And you could very well talk of an angular momentum algebra, where all the structure constants were actually real. Right? That would be very easy to do. Instead of using J1, J2, J3, just use IJ1, IJ2, IJ3. That will give you the algebra where all the structure constants are real. This is important. Structure constants depend on your choice of basis. So it may be possible in a complex vector space sometimes to choose a basis such that all the structure constants become purely real. In such a case, you can always also choose a basis where all the structure constants become purely imaginary. These two are essentially the same thing. They differ by an extra factor of I in the basis. Okay. So the angular momentum algebra that we have is basically from a complexification of the Lie algebra. It's really a complexification of the Lie algebra which comes from the group SO3. And from that, we have our familiar commutation relations. Any questions so far? Now, there are several points to be made here. We are going to complexify real algebras primarily because that will give us access to complex number scalar field, which actually will allow us to have matrix representations made of complex numbers. Why is that an advantage? Because now I am guaranteed that I can always solve the eigenvalue problem. That's one of the reasons. If you stick with real numbers only, then you may not be able to solve eigenvalue problems or matrices written with purely real numbers, right? Matrices which have purely real entries may have complex eigenvalues. In fact, may have all eigenvalues complex. Is it okay? Is it right?
Yes, sir.
Okay. So having said that, so for example, simply this matrix 0, 1, 1, 0, a purely real matrix, you can easily see there is sum of eigenvalues is 0 and product of eigenvalues is -1. And that really tells you immediately the eigenvalues of I and minus I. So eigenvalues, eigenvectors, etc. This cannot be talked about if you stick to real numbers only. The complexification actually gives us much more freedom. Once you deal with complex numbers, every complex value matrix, square matrix, not every one of them can be diagonalized, but at least you can find out their eigenvalues. When I say find out, I don't mean it's easy to find out or something, but it's just possible. Real eigenvalues will exist. Sorry, real or complex eigenvalues will exist. So complexification is a nice process, it's useful. But very often when we are dealing with a complexified Lie algebra, we might want to go back to the original Lie algebra. If I started with a real Lie algebra and then complexified it, you know fairly well that what you started with. But if you start with a complex Lie algebra, now there are several issues. One is the complexification of L, a real Lie algebra, to L tilde is always unique. So if you do complexification here, for a given L tilde is always unique. But the other way around, things may not work. The Lie groups SO3 and SO21 have Lie algebras, corresponding Lie algebras, which are written with smaller letters, that is small SO3 and small SO21. It turns out, okay, they have different Lie algebras, different real Lie algebras. It turns out, and you cannot make their structure constants match by changing a basis. But if you complexify them, both of them will turn out to have the same complex Lie algebra at the end. Now I will give you this as an exercise to show. I'll give you the SO3 commutation relation, which you should already know. SO3 has the same commutation relation as SO2, the angular momentum commutation relations. SO21 has similar, but there's a minus sign. There's a change in sign in one of them, not in all of them. And SO3 and SO21 cannot be obtained from each other. They're not possible. It's not possible to change your basis and just go from SO3 to SO21. However, when you complexify them, it turns out that the complexified version of both are actually identical. So that's the problem. The problem in the sense going back from a complexified Lie algebra to a unique real Lie algebra whose complexification it was may not be possible. It may not be possible to get it uniquely. It's even worse in a sense that if you have a genuine, suppose you started with some complex Lie algebra. You started there, you didn't start with the real Lie algebra and then complexified it. You just started with the complex vector space on which you have defined a bracket. In general, for a general choice of basis, of course, now the structure constants could very well be complex. Okay. But what's more important is sometimes it's possible that it would be impossible to get a basis in which all the structure constants become real simultaneously. So in a general complex vector space, for a complex Lie algebra, it may very well be possible that you will never get real coefficients or all structure constants real. And then you are sure that this kind of a Lie algebra could not have been obtained by complexification. Okay, so there's no counterpart for a real Lie algebra hiding behind the scenes. That way, it's still better, but sometimes it may be a problem that there may be multiple real Lie algebras which gives rise to this. So far, any questions? Okay, next. For real Lie algebras, we have seen several auxiliary notions like subalgebra, ideal, factor algebra. I'm just summarizing what we have talked about. Abelianness. Is a Lie algebra is abelian or not? The commutator subalgebra or the derivative subalgebra, derived subalgebra. Then we have the ideas about solvability, nilpotency. So you can take out solvable Lie algebras, nilpotent Lie algebras, simple, semi-simple, etc. We define each of these ideas for real Lie algebras. But it's very easy to see that you can equally well define these for any complex Lie algebra, not necessarily just for a complexification. But for any Lie algebra, real or complex, you can define these notions. The definitions would go almost hand in hand. And frankly, we need to worry about connections. So I will leave you to worry about why these are true. Okay, if a Lie algebra L tilde is a complexification of L, if L is abelian, what can you say about L tilde?
Should be abelian because for a basis structure constants are all zero.
Good. That's one possible way of saying it. The other possible way of saying it is just start from the defining bracket in the first place. X plus iy, comma u plus iv, the bracket, is defined essentially using combinations of xy, xu, xv, etc., etc. Each of these brackets will vanish, so you will get zero. And so if L is abelian, then L tilde is abelian. What about the other way around? If L tilde is abelian, the complexification is abelian, does that tell you that L is abelian? That is, if L tilde is abelian, you take any two of its elements, take their bracket, you get zero. What about L then? The Lie algebra which you complexify to get L tilde. What about that? No, this should be very easy.
It should not be true. If L tilde is abelian, then it doesn't imply L is abelian.
Okay, let's see. To check whether L is abelian or not, you should take two elements x and y of L and find their bracket and show that that's zero always, right?
Right.
But x and y, aren't they elements of L tilde as well? Because what is an element of L tilde? It's x plus I something else, some other vector, two vectors, right? But null vector is also a vector. X plus I times 0, which is same as X. It's an element of L tilde. So, because L tilde is abelian, this should definitely follow both ways. Well, X by bracket is also a bracket in L tilde, and every bracket in L tilde vanishes if L tilde is abelian. So this bracket should vanish. Or if you want in terms of basis space vectors, there is one choice with L tilde is abelian. There is definitely one choice where its basis coincides with L. And because L tilde is abelian, every one of the basis vectors commute. So you have zero such constants. Such a constant is the same in this case for L as well. So what about solvability? If L is solvable, what does that tell you about solvability of L tilde? This takes a bit of thought, so I will urge you to think of a proof of this. Just think about it. It's pretty straightforward. Just go by the definition. Actually, it works both ways again. If L is solvable, L tilde is solvable, and vice versa. Funnily enough, L being simple does not imply that L tilde is also simple. So, think of this. Why they are solvability is actually very easy to figure out. This issue with simplicity that you can have a situation where L is simple, but L tilde is not simple. That takes a bit of thought. But you should be able to figure this out. It's not very difficult to do. Okay, now that we have complexified our Lie algebra, or we have talked about complex Lie algebras in general, then we can, and we have already introduced all these issues about semi-simplicity, simplicity, solvable, etc. So now we are in a position to actually state this very important theorem, which we will state and almost immediately forget because we will never really use the full power of this theorem. The theorem, which is called Levis splitting theorem, actually says any Lie algebra, real or complex, or split up into a symmetric sum is actually not really right. But it can be written as. Because when you say split up into, then you're not really talking about the sum. That's theorem number one. Every Lie algebra actually is solvable and a semi-simple Lie algebra. But what makes it even more important for us is another result due to Cartman, which is every okay, I said a while ago that we define simple algebras to be non-abelian. We leave abelian algebras out of the definition when you're talking of simple algebras. If you did not do that, if you just define simple algebras as something which has no non-trivial ideals, then this statement would have to be direct sum of non-abelian simple algebras. So depending on the book, some books define simplicity as explicitly stating that they are non-abelian to begin with. Some books actually don't do that. If you are not defining simplicity by also demanding that apart from having no non-trivial ideal, the Lie algebra is actually non-abelian. If you're not doing that, then here you will say direct sum of non-abelian simple algebras. Means the same thing in both cases. And again, the work of Karka, Weil, and others tells us we have a complete this classification is based basically on some arguments like commutative-like arguments, which essentially is the kind of arguments you have actually used in a lot of times in quantum mechanics. Essentially, the same kind of arguments, used judiciously, of course, can lead you to the result that you can actually completely specify all possible simple Lie algebras. There are infinitely many of them, but they all come within 4 or 5 classes, except for a few exceptional cases. In any case, you can actually completely write down all possible simple Lie algebras, which means semi-simple part of every Lie algebra is completely known. That is, you know all possibilities. The solvable part, we are still not so sure. We don't know of a classification scheme that will give us all possible solvable Lie algebras. But as long as you're sticking to semi-simple Lie algebras, and that's what we are going to do in physics most often. A semi-simple one can always be completely classified. You can actually write down what are the possibilities, and your semi-simple Lie algebra will have to be one of the possibilities. Okay, that's the power of the theory of Lie algebras. You know all the possible avenues open to you, even before you start doing it. So we are going to explore the Karta and Weil and others' work. As far as the classification of simple Lie algebras is concerned, in order to do this, we will need some results, some of which we are going to sort of assume to be true, some of which we are going to prove. But before we go any further, let me at least make amends for something that I said earlier. I've already told you that we need to correct that. Because when I uploaded the video for that part, I left out that large amount of discussion at the end. Simply because, well, you could say that I'm doing it because I'm trying to hide the fact that I was completely confused there, which is true. But also primarily because that particular discussion led nowhere. We were so I was so confused that I did not really get to any concrete conclusion in that part. You remember what I'm talking about? What was that I was talking about? Which part? Anybody remember that? The metric or the matrix GJK that we talked about, matrix elements. And I was trying to talk about that as a metric and found that there were some inconsistencies between the standard metric on the space of matrices and our thing. But let me just clear the air on that. I was right in the sense that the formula I was obtaining was different from the formula in the books. But I was right simply because of a wrong reason. I was trying to think of that as a genuine inner product. It is simply not. So basically what is done here is that you define a bilinear form, not an inner product. This is the important thing. but often called the killing product or the killing, is called the killing form. Nothing murderous, it's just the name of the person. It's also often called the killing product, which is one of the reasons why I was so confused. It's a bilinear form, but meaning it's something which will give me a number from, it's a binary operation which takes two entries from your vector space, in this case from your Lie algebra, and produces a number in a bilinear fashion. So this is killing form. Let's say A comma B, not a linear product. So let's say, so that you don't confuse this with a linear product, let's say K of A comma B. This is a real number. Takes in two elements A and B from my vector space. Could be the complex vector space L tilde or could be L. Both of these are Lie algebra elements. And it gives me a real number. And why do I call it a product? Because it's bilinear. Not an inner product, but a product. In other words, K of A C1 B1 C2 B2 is K of A B1, which is a real number times the number C1 plus C2 A B2. This linear in this factor is actually also linear in the other factor. It's a product. It's like all other products. In fact, it's like the inner product in the sense that it is like this. It's symmetric. However, K A comma A is not necessarily equal to 0 in general. And of course, it being neither does it being 0 imply that A is the null vector. Okay. So you just are imposing bilinearity. Linearity in any one factor is enough because of being symmetric. Linearity in one factor implies linearity in the other factor.
So it's not necessarily non-singular.
Not necessarily, but you will see that it's being non-singular has special. Its being non-singular actually has special implications on what kind of Lie algebra it is. Okay. In fact, whether this is singular or not actually allows you to distinguish between semi-simple Lie algebras and other kinds. That's why it's very important. But that is what I'm going to talk about in the next day. I will just show you the definition, the specific definition. Of course, what I wrote down was for any bilinear form. The specific form is this. KAB is defined to be, well, remember you have a regular representation which can also be thought of as a matrix representation. And you will form the matrices TA and TB from. So T and TB are regular representation matrices of A and B. And the definition is simply this. Take the case. This is where I screwed up, right? Why? Because I assumed that because this is, I forgot that this is just a bilinear form, because it's often called also a metric, or the corresponding thing is called a metric sometimes, or the killing metric. I forgot that this is really not a metric, really not something which comes from an inner product. So I was using the standard inner product on the space of matrices, TA transpose TB, rather than just multiplying TA by T. TA transpose TB guarantees the last condition, guarantees that you are going to get a 0 if and only if the TA, the matrix, is 0, or hence the original vector A is 0. Right? Just let me just show you the last part of the calculation where I completely screwed up last time. This quantity Gij is defined to be K of the two basis vectors Ei, Ej. And of course, the reason why you do that is K of any A and B is K of Ai, Ei, Bj, Ej, right? Any Lie algebra element is a vector. It can be written down in terms of basis vectors. So can be. And because of bilinearity, you can write that as Ai, Bj, K of Ei, Ej. So
Sir, what
Gij.
is,
Yeah, what is
what is TA?
TA? We
TATB?
talked about regular representation, right? So do you remember that?
Yes, sir.
The Lie algebra always has a regular representation where A gets changed to add A, where add A is an operator which acts on the space of linear operators on the Lie algebra itself, and add A acting on B. This is a set. Add A is a linear operator which acts on the Lie algebra itself, acting on B due to A bracket B. So that's the adjoint operation. That gives you a linear operator. The corresponding matrix is TA, the regular representation matrix element. This is a linear operator, right? Every linear operator has matrix elements.
Okay, sir. Okay.
And that KEI is trace of TI, where TI and TJ are the corresponding matrices. And we actually had worked out earlier the TI from the definition itself. TI is the matrix whose KL element is CKIL, the structure constants. This is something we have already worked out before. Okay. So what is trace TI, If TI is KLth element times TJ is LKth element sum together, so simply CKIL, CJKL. So this was what was confusing me, because earlier I was thinking in terms of matrix, a proper metric, that is a proper inner product. So instead of taking case of TI, TJ, I was thinking of taking case of TI transpose TJ, which is not what you are supposed to do, and that would have given you the wrong result. This is exactly the correct result. This particular matrix that you form by taking GIs together, this is going to be very important for our work. In fact, whether the bilinear form is singular or not depends on whether this matrix is singular or not. And Carta gave us a criterion which I'm not going to prove. The proof is not too difficult, but it's a bit lengthy and not really essential. Telling us with how you can tell whether a particular Lie algebra is semi-simple or not by looking at the determinant of this matrix Lie. We are going to discuss these issues and further calculations in the next class. Any questions at this stage?
Sir,
Yeah.
so if it is not a metric, Gij, then the vector space in which that generators lie, it is not metric. There is no metric over there.
There may be a metric over there, we're just not using it. There is a metric over there, right? There is a, after all, you can define, since TATB are matrices, and you have an inner product between matrices, that is TH transpose TB. I could definitely use that to define an inner product of two vectors. So I could use, instead of killing form of A comma B, I could define the inner product of A comma B to be trace of TA transpose TB. I could do that. And I would get an inner product. And that would be a genuine inner product. It's just that in this case, that genuine inner product is not that useful. So we don't spend time discussing that. What is more useful is this one. Despite not being an inner product. Look, every finite dimensional vector space obviously has a trivial inner product. You can just define A1, B1 plus A2, B2 plus A3, B3 up to up to n, Bn to be an inner product if you're dealing with real vector spaces, right? Can't you? But when you say your finite dimensional vector space, which is not an inner product space, you don't mean it cannot be made one. You mean that you don't care about the inner product. Okay. When you develop the theory of the vector spaces, you first define vector spaces. You talk about properties for which you just need the vector space property. You don't need the inner product. Then you introduce an inner product on the space. And there could be infinitely many choices for inner product. There are. So when you're talking of properties under an inner product, you're talking of something which works for any inner product. The precise values might depend on that particular inner product you've chosen. In this case, I'm just choosing to ignore the fact that there is an inner product that you can put as use, simply because that turns out not to be that useful. In this context, this particular thing, the killing form, this bilinear form, is more useful. That's it.
But sir, but we need to introduce some sort of connection between that covariant thing and a contravariant thing, right? That would,
Not really. First of all, there is no such thing as covariant or contravariant here. You do have upper indices and lower indices. So we have the CKIJ. In fact, that's actually an important point that we are going to cover the next day. We have this CKIJ. What kind of symmetry properties do you know about CKIJs?
antisymmetric with INJ.
It's antisymmetric in ING. No problem. No such thing as with K, right? K is something entirely elsewhere. It has to be antisymmetric in INJ because it's EI EJ's bracket which gives rise to this. Antisymmetry of the bracket makes it automatically antisymmetric in IJ. However, if you use G, this G, not the metric, but this bilinear form, to lower this K, so define it like this. Or actually, you could write GMK, but that doesn't matter because GKM and GMK are the same. And you define this to be C, a new C, with lower indices, all lower indices. You did that. Okay. It will turn out, and that's what I'm going to prove next day. It will turn out that this CKIJ is antisymmetric in all the indices. Completely antisymmetric. Okay. Right? So this actually tells us that the number of independent CKIJs is actually less than what just the antisymmetry in INJ would tell you. Now, is this lowering contravariant to covariant? The answer is no. There is no contra-co thing here. But you are pretending to do the same thing and you are ending up with something useful. The CKIJ has all lower indices, is completely antisymmetric. So, of course, say for example, in 3 dimensions, then it turns out that there is, if this was 3-dimensional D algebra, it turns out that there will be only one independent structure constant. All the others will follow from that. That's complete antisymmetry for you. Because this, in 1 dimension, it will tell you the C1 to 3, C2, 3, 1, 3, 1, 2 will be the same. 3, 1, 2, see 3, 2, 1, 2, 1, 3, and 1, 3, 2. They will also each be the same but negative of the previous one. And whenever 2 indices are repeated, you're going to get 3. Basically, what you're saying is in 3 dimensions, what you're going to get essentially is apart from a sign possibility, you are actually going to end up with the SO3 algebra or the angular momentum algebra.
That means we are not caring about the contra-co because we are dealing with the semi-simple groups. Right?
No, first of all, there is no contra. What does contra-co really mean? It means that your contra and co talks about transformation properties when you change your basis, or when you rotate your coordinate system or do something, carry out a non-orthogonal transformation on your coordinate system. What happens to vector components? We are not bothered about that here at all. Okay? But taking a leaf from that book, we have actually used the upstairs downstairs rotation. That actually works nicely. And again, taking a parallel to lowering an index that you do when you're really talking about contravariant or covariant indices, you end up with this thing where all the 3 indices end up behaving identical. This is something we are going to prove in the next class. And then we will need to use it. It's useful, that's why we do it. Not because there's an underlying contravariant covariant structure. You could cook up one, but that's not what you really are interested in right now. Or you could say lowering or raising could be defined even without a metric. That actually is an important point, by the way. Remember, even if you were dealing with things like standard general relativity or standard tensor, suppose I had Tijk and some matrix CMI, this combination, and this CMI were at, say, 2-0 tensor, and this was a 1-2 tensor. What kind of an object, or actually, when I say this is a 1-2 tensor, I mean these are components of a 1-2 tensor. These are components of a 2-0 tensor. When I contract it like this, what kind of an object do I get?
3,2.
Really? We would get 3,2 if you were doing an outer product, but remember you are doing an inner product here. So what do you get?
3,0.
You get a 3,0. There's 3,0 tensor. That's what the inner product does. Now, this 3, tensor you would not call T. That would have M, J, K as indices, each one covariant indices. I is, of course, a dummy. They are no longer actual indices. But you could call it R or M, J, K or something. Okay. If the CMI were not the metric, you would not call this the covariant version or the lowered index version of T. You would say it's a new 3, 0 tensor that you're opting. Right? Only when you're using GMI Tijk would you say this is TMJK. That's the notation you use, right? You will say this is the 3, 0 version of this 1, 2 tensor, where I have lowered this I index and made it M. The lowering of the index and transformation properties that stay valid even if you were to use an arbitrary 2-0 tensor, not just a metric. But why is this the covariant version and not any other one? Why do you have to lower with GMI? Okay, this is something I'm not going to tell you. You have to figure out. Why is it that when you take let's forget about Tijk, let's start with the vector Ui and do GGI on that. The resulting object, which is the covariant object, is called Ui, the same vector's covariant version. Whereas if you had any 2-0 tensor and done this would have been, sorry, Vj, Uj here, this would have been the jth component of some covariant vector, definitely. You just don't call this the covariant version of this U. Now, why is that the case? Why is it that this one you call the covariant version of this U, and you just say this is a covariant vector which you have built out of U somehow? Okay, I'm urging you to think about why that is true. Okay. Anyway, I've long overshot the time. So let's stop today. We are going to discuss this. Not this, but this is something you have to figure out yourself. What's so special about this particular thing? Why using the metric is so special? Okay. Let's do one thing first.